Good morning and welcome to the Industrial Heating Equipment Association's webinar series on sustainability and decarbonization. I'm Kelly LeCount, IHEA's Education and Training Manager, and on behalf of the association, we thank you all for joining us. We're pleased to have a terrific slate of presenters for today's webinar titled Ongoing Sustainability Industry Best Practices. I'm happy to announce that IHEA will continue the sustainability webinar series by adding new titles each month through 2024. Next month's webinar, Alternatives to Combustion, is scheduled for September 21st. Registration is now available. Watch for more of our sustainability webinars to be added very soon. Before we get started, I'd like to remind everyone that all attendees are on mute, so if you have any questions along the way, please type them in the questions panel. The speakers will address them at the end of the webinar. All attendees will receive a brief survey after the webinar. It will take just a few moments to reply. We appreciate your feedback as IHEA continues our critical initiative for the industrial heat processing industry. One last announcement, this webinar is being recorded and will be available in the sustainability area of the IHEA website within the next few days. You will receive an email once this link is available. Now I'll introduce our presenters for today's webinar. Michael Stowe is a Senior Energy Engineer with Advanced Energy. We have Brian Kelly, he's an Application Engineering Manager with Honeywell Thermal Solutions. Keenan Cocaine is a Corporate Sales and Applications Manager with Bloom Engineering Company. And Jeff Rafter is the Vice President of Sales and Marketing with Celis Heat Technology Company. All of our presenters today are members of the IHEA Board of Directors and or speakers for IHEA training seminars. Thank you all for being here. Michael Stowe will start us off today. Michael, it's all yours.
Thank you, Kelly. Appreciate that. And we have a great line of speakers today with lots of applicable, hopefully things that you'll recognize that are actually being implemented. And I'm just going to start off with a little bit of introduction, a quick review. Some of this we've repeated a couple times, but just a little bit of carbon, greenhouse gas background. We'll talk a little bit about continual improvement, and then we'll get best practices, stories from the field, from actual process heating vendors, and talk about some of the things they've been working on. So thank you for joining us today. Talk about a little bit about the energy carbon connection. We tell people this all the time. The best way if you want to manage your greenhouse gases and your carbon is to manage your energy, because most of the greenhouse gases, and if not all of the carbon in your greenhouse gas emissions comes from consuming energy. This is the big picture of energy. Yes, I know this is an eye chart, but I just want to kind of make a couple points here. If you look at the left-hand side, this is a Sankey diagram, and the left-hand side is the total of all the energy consumed in the United States in 2021, which is almost 100 quadrillion BTUs. Quadrillion is 15 zeros, so it's million, billion, trillion, quadrillion. And these are the sources. So this adds up to 97.3, and then it breaks apart and goes across, and the other side adds up to 97.3. So this is how energy flows through the United States. A lot of energy, as you can see, is used to generate electricity. And looking at our areas, commercial buildings, but primarily industrial, you can see not that much of industrial is electricity. There's quite a few fossil fuels still being consumed, natural gas, particularly, and petroleum products, a little bit of coal, but also electricity. I want to make the point that electricity is not squeaky clean. It's not all nuclear and hydro and solar. There's quite a bit of coal and natural gas still in the electrical generation for the United States. And this will need to change as we move forward into a greener environment. And hopefully we can reduce some of the consumption of fossil fuels in industry. And of course, you hear lots about electric vehicles down here. So that's kind of a really big picture of where the energy goes. And again, we're looking at, how can we reduce our greenhouse gases through managing our energy? One thing to really think about is energy efficiency in terms of greenhouse gas reduction. This is what you pay for. You bring energy into your sites. You manufacture, you have a commercial building, a hospital, a college campus, an industrial process heating site. And this box that's your system, that's your building, that's your process, and you pay for natural gas and electricity and bring that in. And you want to get as much of that energy as you can to add value to your product. and reduce these losses to an absolute minimum. And that's what energy efficiency projects can do. And also, again, energy efficiency improvements will improve or reduce your carbon footprint. Energy and carbon are directly connected. It's chemistry. There's no way around it. This is the way the world works. If you take methane or any fossil fuel organic carbon molecule with carbon and hydrogen in it and mix it with oxygen and combust it, you will get carbon dioxide and water vapor. That is the way the world works. This is methane, and if you think about, that's the pure equation, but if you think about typical combustion, you have air. So you have nitrogen that just kind of passes through, no reaction. Air is about 20% oxygen, 80% nitrogen, and a lot of little odds and ends. But again, methane plus oxygen gives you carbon dioxide and water vapor, plus the heat. You get the heat, that's what you want. The heat of combustion to do the process, to run the furnace, the oven, the melting, the baking of the cookies, whatever the process may be. But this is the problem, you know, combustion, and this is gasoline, diesel fuel, methane, coal, makes carbon. Thus, carbon footprint, carbon is the biggest contributor to greenhouse gas emissions, and we'll see that in a minute. Electricity may be a good alternative to combustion for a heating process, but electricity is not magic. Electricity is not free from carbon footprint impact. And you can see this is the 2021 national energy mix of all the electricity generated in the United States, and a full 58, 59% is still generated from fossil fuel. So if you electrify a process, yes, you might eliminate a natural gas consumption, but your electricity is going to have some component depending on your regional location and how your electric utility generates their electricity. You may have something that's very heavy coal or very heavy natural gas, or you may have an electrical utility that's very heavy on nuclear and hydro and renewables. So it depends on your location. And looking at that, this is a map of the United States and Alaska and Hawaii. Different regions have different amounts of carbon, and these numbers you see in the big boxes, that's pounds of carbon dioxide created for every megawatt hour of electricity produced. So you can see there's a wide range. California is very, quote, clean and green electricity versus, look at Hawaii is 3 times the value of, or the amount of CO2 produced per megawatt hour of electricity. So this varies regionally. So if you have a plant in San Diego versus a plant in Texas versus a plant in Minnesota, your contribution of carbon from the electricity that you consume is going to be different. Carbon combustion from natural gas, that's the same everywhere. It doesn't matter. You burn natural gas, you're going to get so much carbon out, period. If you consume electricity, the carbon content of your electricity will vary regionally. And there's quite a bit of variation. Those are just some example numbers. Greenhouse gas scopes 1, 2, and 3. Why do I have a picture of a John Deere tractor? I just want you to think about, from an industrial manufacturing point of view, all the processes, the process heating, the source materials that it takes to build a complex machine like this. You got to get iron ore out of the ground and make steel. You've got aluminum, you've got rubber, you've got plastic, you've got copper wiring, you name it, you've got it. And lots of processes that consume electricity to make and assemble this. And there's various scopes of greenhouse gases that contribute to this, but think about the carbon footprint of making such a machine as this and all the processes it takes. Just kind of keep that in the back of your mind. So there's lots of greenhouse gases. There's 7, we call the 7 major greenhouse gases. And the way this chart works is they took carbon dioxide, because it is so common, and say if carbon dioxide has a score of 1, these other gases, what are they relative to that score? And this is the 100-year global warming potential. So if carbon dioxide stays in the air for 100 years, it's going to warm the atmosphere because it captures the sunlight. Sun comes in, it heats the Earth's crust, it radiates, but it can't get back out to outer space. It's captured. It's the greenhouse effect. It's just like building a greenhouse. It can be 103 degrees inside a greenhouse on a cold winter day because the sun shines in the greenhouse, the heat can't get out. But look at some of these. Methane, if you combust methane in a process and get carbon dioxide, that's great. If you leak methane uncombusted, it's 25 times worse. So you hear people talk about cow manure, pig manure, letting all, methane going up into the air directly, or methane leaks. It's much better to flare methane than to let methane just leak. It's much worse. But look at sulfur hexafluoride, 22,800 times worse than carbon dioxide. Now, again, there's not much of this around. It's pretty rare. But hydrofluorocarbons, perfluorocarbons, those are all the refrigerants in your air conditioning units. Air conditioning's everywhere. So there's a lot of this stuff out there. And if it leaks to the atmosphere, it can be very, very potent in terms of global warming. But why do we call it carbon footprint? Because carbon is the big deal. Carbon is the big one. This is all from combustion in cars, internal combustion engines, boilers, generating electricity, all the process heating that a lot of the IHEA companies build and supply and their customers. And methane is second. Nitrous oxide is pretty big, and then the fluorinated gases, and you could see some of those others don't even have enough pie. But this is why it's carbon footprint, because over 3/4 of the gas emissions from industrials, or this is from US, not just industrials, come from carbon. And industry is about 1/4. So you can look at commercial and agriculture is about 1/4, transportation is a little over 1/4, electric power generation. So we're in this area. Most of us operate in the industrial area, and industry is responsible for about 24% of all the greenhouse gas emissions in 2020. Greenhouse gas scopes. There's 3 scopes. There's more than 3, but there's 3 primary scopes. Scope 1 is that's that carbon equation. Methane plus oxygen gives you carbon and water. If you're burning, if you have combustion on your industrial site, if you make equipment that uses combustion and people use that, that is scope 1 carbon, direct emissions. You burn it on your site, the carbon goes in the atmosphere. Or you have a lot of vehicles that you're operating with gasoline to run your business. Think about the US Post Office. They have 232,000 vehicles, and most of them are internal combustion gasoline or diesel engines. That's the internal combustion, that's direct emissions, that's scope 1. Scope 2 is all the electricity that you buy. It can be other things, but like if you buy steam or chilled water, but mostly it's electricity. The electricity has to be generated somewhere, and you use it, but it has to be generated somewhere, like we said, with a regional carbon footprint from the generation equipment, and that's your scope 2. Scope 3 is everything else it takes to run your business. Scope 3 is raw materials, how do you get the materials to your plant? And then you build it at your plant, that's scope 1 and 2, and then you ship it, and it's used out in the field, and that's all the downstream. So all the upstream impacts and downstream impacts of your product, that's scope 3. So again, thinking about the tractor built at a plant, it's got scope 1 and scope 2, but it also has scope 3, which is like getting the iron ore out of the ground, making the steel ingots, getting the ingots rolled into bar, shipping the bar to the John Deere plant, and on and on and on, as you can imagine. So a little bit about continual improvement. One of the things that we want to encourage people to do that are looking at energy management and carbon footprint is to have a continual improvement process. This is an example of a company we work with. It was a wastewater treatment plant, and this is kilowatt hours per million gallons of water processed over 18 months. And they were around 7,000 kilowatt hours per million gallons, and they did some energy management, implementation, some energy projects, and they really got this, initially really came down pretty quick, and then it kind of leveled out. It got a little harder to keep improving, but that's a great trend, and that's what we want to encourage. And if you think about an energy management pyramid of various levels of managing energy, there's just basic energy management where you say, okay, we're going to put our energy bills in a spreadsheet. We're going to track how much energy we're using. Then you may want to advance to some other programs. There's ISO 50001 is the energy management standard for international standards. And there's a 50001 Ready program. There's a Better Buildings, Better Plants program. There's lots of stuff available on DOE that you can use to help manage your energy and start improving. Then you can get full ISO 50001 certification, and superior energy performance is like the top of the mountain. That's a DOE program. It's very rigorous, very challenging. So fewer people do this, many people do that, but as you go up this pyramid, it becomes more commitment, more resources. But the key for companies, either IHEA member companies or IHEA customers of members, or anybody that does process heating or heavy industry intensive, energy intensive industries, the key is to figure out where is your point A and B. It doesn't matter what somebody else is doing. You can say, we don't really have anything. Let's start with basics, and we want to move up here to really improve and implement some energy management. So wherever you are, start where you are and improve from there. Again, all of this that you do to manage energy will only help you to be more sustainable, to meet your environmental, social, and governance goals, to meet your carbon footprint goals, to be net zero by 2040, or whatever goals you may be facing as a company. Again, ISO 50001 is the energy management standard. Is the 2018 version is the latest version. It's a great document. It's not easy. It is challenging, and there's quite a few things you have to do to meet this and get certified. 50001 Ready is a program of training and implementation for 50001, sponsored by DOE, that you can do without getting certified. And it's based on the Plan, Do, Check, Act. And in a nutshell, this says you say what you're going to do to manage energy, and then you do it. And then a little bit later, you check and see, are we doing what we said? And if we're not, we're going to act to fix it, and then we're going to repeat. This is not a project. This is a process. Plan, Do, Check, Act, Repeat. And that's where you get the continual improvement. And you build this into the day-to-day business activities that you have, and it's just part of what you do. Instead of being something extra to do for a project, this is just how we do. Plan, Do, Check, Act, our energy, and repeat. Energy 50001 is very goal-oriented and data-driven. It's measured. You measure things. You intentionally understand your improvements, your targets. You measure baselines. You measure where you are today. You look at your baseline and you see your improvements. It's very data-driven, which is very beneficial. And again, this all ties into carbon. 50001 Ready, again, is a great tool. It's got all kinds of available source material. It's all free. The DOE runs a cohort program where you can be a member of a group of 5 to 10 companies that go through a training program over 6 to 8 months, where you get to be taught about 50001 Ready. It's all free. The stuff you download from the tool is all free. It's a great resource. And then Better Climate Challenge, the Oak Ridge National Labs and DOE has started a Better Climate Challenge. And in this case, you can sign up with your Scope 1 and 2 emission reductions, and you have a baseline, and you set goals, and you work with a technical assistant persons from DOE that can help you with your goals. And this has a lot of tools. And actually, the previous session we did talked about a lot of the tools that are available from DOE. All free, all free. Okay, that's a little background. We're going to shift over now and let some of our industry folks tell us some of the stories that they've been seeing from the field and some of the implementations that they've been doing. First off, we have Brian Kelly, and Brian, I'm going to give you control and you can take it away.
Okay. Or what? Come on. There we go. So, what we want to talk about here is when you start talking about sustainability, decarbonization, really when we talk about it in the thermal area, and Michael has more reaches out into a lot of the energy sector than some of us that are in the combustion business. Not that we won't be looking at other assets as well, but sustainability as relates to thermal processes really relates to your consumption of fuel. If you currently fire a fossil fuel, most common is going to be natural gas, but it can be oil, it can be other fuels, propane, things of that nature. But generally, it's going to be natural gas. So if you reduce the amount of that fuel burned to your heat process, is directly proportional to the reduction in CO2. So when you look at your furnaces, your firing assets, your furnaces, heaters, start thinking about what you can do on a continual basis to improve your process to reduce fuel, and therefore reduces CO2. So Efficiency. Michael mentioned efficiency. So that's the more efficient you are, the less fuel you burn, right? The more efficient you are, the more of that resulting heat from burning that fuel in your system is getting into the product, heating the air, drying the baking rolls, whatever it may be. So I'm going to hit some real simple guidelines here. Most people, it's like when you need to look at maintenance and tuning, been plenty of places that, hey, when's your last PM? It still runs. They push the button, it lights up, they're good to go. So some of this is actually will add to your bottom line too, but also keep you more efficient, right? Simple maintenance, upkeep of the equipment, look over the burners, the control systems, but even the units themselves. If you start seeing hot spots on your furnace, or there's holes in the furnace that you can actually see something radiate out of, that is making you less efficient. That means heat is getting out of that box and going to the atmosphere. It's wasted fuel. And regular tuning of the thermal combustion systems, you start look at, hey, where are we at? Do you have the records to know where your, say, excess air is at? But another part of that is keep some records. So depending on what your operation is, who's maintaining your equipment, they know where those burners were set, the PID loops were set, all the critical information that makes you effectively heat your product in the shortest time possible. But just a simple example here is that if you've got, might have a little delay here. There we go. Come on. Okay. This is a simple energy savings calculator. So I assumed our exhaust temperature is 1800, 35% excess air, our initial state. So no flue gas recirculation, oxygen's 20.9%. If we tune that system from 35% excess air to 10, you'll see the resulting energy savings is about 17%. That's not insignificant. There are processes that require excess air at certain times, so you've got to look at your process and what your product can take as well. Air fuel ratio control. The ability to maintain a tighter ratio between your air and fuel throughout the whole range of your combustion system is going to increase your efficiency and reduce fuel. Again, some processes require different type air fuel ratios throughout a process. But along with that is looking at the actuators that are going to look at that variation, because in the example that I'm going to bring up here is you've got your blue mass over on the left, and you see our temperatures around the set point's 1350, or at least that's where they were averaging. Maybe that was not the set point. So this blue area here was a linked valve system with just a pretty standard actuator. When they upgraded the system to what we call a parallel positioning system, so independent control of air and fuel, and you set an air fuel curve, you can see the variation in temperature reduced greatly. And this can result in better product as well as emissions and performance and possibly even throughput. So don't ignore that. It's an important part of it. There we go. Some things to consider. A lot of the US is your combustion air for your burner systems comes from a combustion air fan. It's pushed in through the system, and it can be a single burner or multiple burner system. And we go from there. Something that's gaining more notoriety. This is something that's been done in Europe for many, many years and in different areas of the world, because their fuel is much more expensive than ours is. But this is another look at not just fuel costs, which these will bring down. This type of technology will bring down, but it also, if you're firing more efficiently, you preheat the air, you use less fuel, that's less resulting CO2. So your options are a variety here, right? On the left here, we've got our heat recovery, which is a main stack heat exchanger or recuperator. So our exhaust is washing over and the cold air, combustion air comes in and heat is exchanged. So we're preheating the combustion air to that burner, those burners, and we no longer have to take the cold air delta P to get it up to temperature. Kind of in the upper right there is a variety of self-recuperative burners. So these burners actually preheat the air within the burner itself. And they can be in direct fired or tube fired situations. Left there is just a simple U-tube, but add a recuperator to that, a plug recuperator, you can reduce your fuel consumption. Actually, in the middle there is a self-regenerative burner. So the burners take turns exhausting and firing and get very good efficiency that way. And just an example on the lower right there is a self-recuperative tube-fired burner. But again, all these burners are looking at the efficiency to increase the efficiency and sometimes certainly improve the throughput of the furnace. And just a last slide here to kind of look at the case study. So this upgrade was a conversion from burners and U-tubes, very, very common, to self-recuperative single-ended radiant tube burners. So we replaced the U-tubes, or they replaced the U-tubes and replaced them with single-ended radiant tube burners. What they saw, because they're now recuperating, they're preheating that air, 18% increased production because they went to ceramic tubes and you can get more heat flux out of those. Hot spots were removed that they saw and caused tube failures, and approximately 30% reduction in fuel usage. And which before everybody, well, as Michael said and I said, translates directly to a reduction in CO2 emissions. So just some considerations. Of course, it's capital, but what you can look in the future is, and there's been plenty of talk about hydrogen and biofuels and renewable fuels. If you have a situation where you may see that in the next 5 or 10 years, burner systems don't get bought every other year, right? So consider it, you work with your combustion system suppliers and say, hey, if we go to an alternate fuel, can we be ready? And with that, Michael, I will exit. Thank you.
Thank you so much, Brian. Appreciate that. Next up, we have Keenan Cocaine from Bloom. And let me make you a presenter and take it away, Keenan. You should have control shortly.
Thanks, Michael. Trying to get control here. Says I have control. There we go. All right, so I just wanted to go over a quick example. A few years ago, we had a client approach us, and they wished to reduce the fuel consumption and decrease NOx from their continuous galvanizing line. Their project goals were to hit an efficiency of about 73%. That was kind of the minimum that they wanted to achieve. They also wanted to, at the same time, decrease their NOx emissions. So I know we're kind of focused on CO2 right now, but you know, a lot of times if you're making a change, and then that is a good time to look at your other emissions. You know, stuff like NOx. It's an additional payback that you can get if you can decrease something else in addition to decreasing your CO2 or your fuel. So anyway, this continuous galvanizing line was heated with W tubes. The burners in the W tubes were a suction only type burner. So basically it had an exhaust blower that created a draft that pulled the combustion air in. So kind of an older design. What we proposed doing, press forward here. What our proposal was to install a push-pull type recuperative radiant tube burner. So instead of having just a suction blower inducing a draft, we were going to add a forced air combustion, or a forced combustion air blower that would add a positive pressure to the combustion air. Basically, what that would allow us to do is utilize a longer and more efficient recuperator. The recuperator would be extended a little bit outside the furnace. So obviously, you wouldn't want to extend it into your furnace and rob heat from your process. But we were able to use a longer and more efficient recuperator to capture more of the heat leaving in the exhaust gases. Just something to point out is that, especially with 3D printing technologies and stuff of today, there are recuperator designs that are available now that were not available 10 or 20 years ago, that have a much higher surface area compared to past designs. So you can get a lot more heat transfer for a given length of recuperator with some of these new and innovative designs. So here's what our predicted performance was. What they had existing was again the suction type only 2320 burners. Those had a gross power input of 186 kilowatts. They were getting an efficiency of about 66.6%, or I'm sorry, 60.6%. So not terrible, but not as good as what we would expect in a more modern application. And the NOx was actually pretty poor. Given that efficiency, that isn't the greatest of NOx. Our proposed solution would actually require 151 kilowatts. Because we were going to be able to capture more energy from the exhaust gases and increase our efficiency, we just needed less fuel. So it ended up being about a 19% predicted fuel savings. And that ended up giving us about just under 75% efficiency, and our NOx was going to be cut by more than half. Our final results. So this isn't at quite the maximum temperature. A lot of times the maximum temperature isn't the everyday operating temperature, but at 140 degrees C, which I think that's somewhere around 1540 or something, 1500 degrees F, they saw a 76% lower heating value fuel efficiency. And that was about a 20% fuel savings, or a 20% CO2 savings for this customer. They also saw a NOx of only about 110 milligrams per normal meter cubed. So if for those of you who work in ppm, that'd be about 55 ppm at 3% O2. So a major decrease in NOx, and obviously meeting the fuel and CO2 reduction goals as well. With that, I guess I'll turn it over to, I guess Jeff is next.
Yeah, thank you, Keenan.
Yeah, Jeff, let me hook you up here, and should have control shortly. Should be coming up now. Thank you, Keenan, and up next, Jeff Rafter, thanks. Should have control shortly.
Okay, Michael, you might want to help me out and advance the slide. It doesn't seem to be working on my end. There we go. Okay, good morning, everyone. Brian and Keenan did a wonderful job there of giving you some examples of CO2 reductions with conventional burner systems. To give the final examples, what we thought we might do is introduce something that's a little more revolutionary technology and somewhat unconventional, but represents some pretty significant opportunities for CO2 footprint reduction. As Michael had presented with the chemistry of combustion and the basics most everyone's probably aware of, most of the time we combust fossil fuels with air as the oxidant source. There is an alternate technology available where we can eliminate the 80% of air that is represented by nitrogen and replace the oxidant by using pure oxygen to burn fuel. This isn't an uncommon technology if you think about oxyacetylene torches, which is fundamentally the same concept, but the advantage for carbon dioxide production is quite simply that it tends to be much more efficient in transferring heat to high temperature processes. That improvement really fundamentally comes from the fact that you've eliminated 80% of the oxidant mass flow that, once it reaches the process exhaust, carries heat out of the process. And so quite frankly, the process does a better job. More specifically, when we look at how oxy-fuel tends to enhance efficiency and reduce CO2, in some processes, the higher flame temperature that's produced by burning fossil fuels with oxygen promotes more aggressive radiant heat transfer to the product or to the furnace. As an example, when we burn natural gas with air, you typically see a flame temperature in the neighborhood of about 3,500 degrees Fahrenheit. When we eliminate all that tramp nitrogen and air, and we burn the same natural gas with oxygen, your flame temperature will spike to over 5,000 degrees Fahrenheit. And given that that heat transfer mechanism is driven by the temperature differential taken to the fourth power, imagine what that does for radiant heat transfer inside an industrial high temperature process. The second benefit of oxy-fuel is, as you saw in Michael's presentation, that oxides of nitrogen are an even more potent greenhouse gas than carbon dioxide. Any reduction in NOx is also a benefit to reducing your greenhouse gas production. NOx can typically be mostly eliminated in oxy-fuel combustion. And obviously the reason for this is quite simply there's no nitrogen in the reaction. By eliminating that nitrogen, the only way you can produce NOx is by having tramp air enter the process. The third point we've kind of already made, and that is because the total stack volumetric and mass flow basis is reduced by 70%, you keep more heat in the process. All flue gas emittance represents a loss if it occurs at anything other than ambient temperature. And of course, as you know, all industrial processes tend to have exhaust temperature that can be recuperated. But reducing that mass flow rate reduces the energy that moves out of the stack as well. So typically when you put it all together and you look at oxy-fuel processes that have been demonstrated now for about 25 to 30 years, fuel usage in high temperature processes can be reduced by 25 to 40% by converting from air fuel systems to oxy-fuel systems. Michael, could you advance to the next slide? Thank you. So first I want to speak about oxygen natural gas firing. Again, this is a relatively simplistic setup where we eliminate combustion air blowers and we convert the oxidant in the reaction from air to pure oxygen. The carbon dioxide production is going to typically be dropped by 25 to 40%. Again, it can be very dependent based on what the application is, how the furnace is designed, how tightly the furnace is sealed. But again, pretty impressive numbers in terms of total reduction of fuel. However, I want to also point out that economically, this does not mean that the total operating cost will drop by 25 to 40% because, of course, the big disadvantage of oxy-fuel firing is that you have to pay for oxygen. So instead of just a natural gas bill, you also have a cost to procure or generate oxygen to fire the process. Typically, once all that's accounted for, we have experiences that say your total fuel savings and your total production cost savings will still land in the 10 to 15% range, but there is an offset to the reduction in fuel consumption made up by the cost to acquire oxygen. Another side benefit is that electrical consumption tends to drop because, of course, we've eliminated combustion air blowers. And if the larger your combustion systems are, typically the more horsepower you're consuming. And of course, the net benefit that we're all looking for, frankly, is carbon dioxide is reduced significantly when converting from air-fired to oxy-fired. One more point I'll also bring forward is that because these systems eliminate all of the nitrogen, the need to seal these systems tightly is great. The more tramp air you introduce back into the system, you're losing some of the potential benefits, both in fuel savings and reducing stack flows. In addition, you don't want tramp nitrogen because, quite frankly, under these high temperatures, it's very easy to convert the diatomic nitrogen to oxides of nitrogen, even though they're not traveling through the flame. Next slide, please. Now, the future looks pretty bright when we think about oxy-fuel firing because, of course, the ultimate end state is to not use carbon-based fuels at all. And I'm happy to report that Celis and a number of other manufacturers are already well on the way to qualifying a number of oxy-fuel burner systems to be fired with hydrogen as a fuel instead of carbon-based fuels, be they oil, natural gas, methane, propane. The benefit, of course, is now, in addition to eliminating the nitrogen, we've also eliminated the carbon. In burning pure hydrogen, there's also some side benefits. Keep in mind that the theoretical flame temperatures we mentioned before with natural gas tend to jump about another 400 degrees Fahrenheit when you make the swap from natural gas to hydrogen. Electrical consumption, again, is also completely eliminated. And at an end game of sustainability, an oxyhydrogen fired furnace philosophically produces no CO2. So from a reduction in carbon footprint and from a total energy efficiency perspective, this is a technology that is coming online today. In the steel industry, there have already been a number of demonstration projects and conversions where they're working on green steel manufacturing processes that are burning hydrogen, and some of those are also burning hydrogen with oxygen. There's also at least one demonstration project that's been started and proven out of Europe, where they're melting glass in a large glass melting system for container glass, high firing the furnace with oxyhydrogen burners. Here again, just like in oxy natural gas firing, oxyhydrogen firing, we still want to also think about augmenting the system to make the system as tight as possible, because tramp air infiltration will somewhat backpedal our goals of reducing both oxides of nitrogen and CO2 production. Okay. So that's it for my slides and presentation on oxy-fuel as an alternative. I'll turn it back over to Michael, close the presentation. Thank you everyone for your time.
Thank you, Jeff and Keenan and Brian. Appreciate that. So I'm gonna just kind of in summary, and we do have a good amount of time for questions if we have some, but just remember that as you have a need to manage your greenhouse gas, or is more commonly maybe known carbon footprint, managing your energy, understanding your energy consumption is a great way to manage your greenhouse gas and carbon footprint. Understanding your energy sources, how you use those and consume those, and the various scopes of the carbon, to inventory those, scope 1, scope 2, scope 3, and so forth. A lot of companies are moving down that road. Right now, it is mostly voluntary in the United States to account for your carbon. It may not always be voluntary. It may become law at some point in the future for carbon accounting or even taxation on carbon, but that's down the road. And great ideas from three people that are in the middle of this industry and really looking hard at this from their companies at combustion processes, alternatives, and getting the most you can out of your existing equipment, which is the right place to start. And then maybe as technology grows and develops, you can increase and improve. But I mean, everybody's not going to go out tomorrow and be able to buy something new, even a traditional burner. But get the best you can energy efficiency out of what you have now. That will impact your energy and carbon, and then move forward. But great ideas and some good thoughts to take away. So Kelly, I'll let you check the Q&A to see if we have any questions from the audience.
Thanks. So the first question we have here, if on-site oxygen generation pressure swing adsorption approach will increase on-site electricity, will that be, let me see, will that be more than the blower electricity savings? If any of the speakers want to address that for us?
This is Jeff Rafter, and I'll tackle that. Yes, typically PSA oxygen generation does take more electrical consumption than combustion air blowers, but in specifically glass melting, if you look at conventional air-fired technology that is being replaced by oxy-fuel, you still tend to generate that 10 to 15% total energy and operating cost savings. So yes, once factored in, that does make a difference in terms of your total electrical profile. But when you look at the whole process front to back, moving to an oxygen fired system over a recuperated air fired system still continues to reduce your total fuel usage and operating cost.
Thanks, Jeff. Next question, does it make sense to look at oxy burning for lower temperature applications where historically use less than 200 psig steam?
It's a little questionable depending on what the low temperature process is. So it's interesting because there have been installations of oxy fuel at lower temperatures, for example, 1600 degree Fahrenheit forging furnaces. There are a handful of those operating and they do generate total savings. But at 1600 degrees, you don't necessarily realize the heat transfer benefit of the higher radiation that you do in something like metal melting and glass melting when you're running at 2400 to maybe 2800 degrees Fahrenheit. It can be done. There's also been some demonstration and research-based work on actually doing oxy coal combustion inside boilers. Because of the obvious benefits of mass flow reduction inside a boiler, there's some thinking that says if you burnt coal with pure oxygen, not only would you tend to make all of the volatiles much more destroyable, I guess is the right term, but by reducing the mass flow through the boiler, you can make a more efficient boiler, reduce the total mass flow, and promote more heat transfer in the primary heat transfer section of the boiler through that high radiation. I'm not aware that any oxy coal is currently being used in production. Again, it's all at the research level, but there is some opportunity for oxy fuel to be used in lower temperature applications. But from my experience, the benefits tend to drop off when you get below, say, 1400 degrees Fahrenheit. If you get into true low temperature process air heating or process stream heating applications, oxy fuel is quickly going to lose some of its benefit.
Okay, great. We have another question here. How does the higher temperatures achieved with oxy-fuel systems affect the life of the furnace? Heating tubes, refractory, etc.
A very good question. Because of the high radiation and the intensity of oxy-fuel combustion, those systems are typically designed specifically for oxy-fuel handling. Oxy-fuel can be a questionable technology for retrofitting because of that. So for example, when we look in glass furnaces and metal melting furnaces, we tend to change the refractory composition to very high alumina refractories because they have to be resistant to the oxidation and have very high temperature resistance. On the alloy side of things, it can be very challenging to have anything in close proximity to the burner. The burners themselves are designed quite differently than air-fired systems so that they maintain, high durability and longevity. But on the good news side, if you look at, like, for example, glass melting, a typical campaign life for a melting furnace is it runs 24 hours a day, 7 days a week for over 10 years is current target for most customers. And oxy-fuel burners are actually meeting those demands successfully. So good long life, but materials of construction all around oxy-fuel systems have to be changed. Very difficult to retrofit.
Okay. Another question here. What increase in scope 3 greenhouse gas occurs when using oxygen for combustion rather than air?
I think probably the biggest impact was actually mentioned in one of the prior questions, which is the cost of oxygen generation. So when you look at total scope, again, you'll tend to see a total savings in operating cost, which can be loosely translated to your CO2. But you tend to see about a 10 to 15% total operating cost savings. Again, every furnace is different, every process is different. But when you look at the scope 3 definition, your total energy usage and your total CO2 production, yes, the cost of generating oxygen, usually driven by electric systems, also has a CO2 footprint, so that has to be factored in as well. Again, usually comes up on the positive side, but to a much lower degree than what you see in the total fuel savings.
Okay. We have several more here. Let's get through them. Could you please compare electrical furnaces to natural gas furnaces?
Yeah, some furnaces by design can be fired both natural gas and electric, depending on the region it's in, what it makes more sense to do. There are some processes that are looking at electrification right now. So in a natural gas furnace, there's a multitude of applications, right, where natural gas can be used. Very low temperature, or let's take a high temperature furnace, heat treat, doing something. If we go electric with that, then, and I'm not a furnace builder, just been around for too long, then you've got to look at how do you introduce that heat in. There's usually elements. The design of the furnace is going to be different to get the heat onto the product, because it's much more it's going to more depend on radiation than convection, unless we start looking at high temperature fans. So it's a very interesting question. It's not too straightforward. Lower temperatures seems to be more of a target, but at the moment, just because electricity can heat air every day, like a heat pump and things of that nature. So very good question. I think if you've got some partners you have for ovens or furnaces, they probably will do a little bit of both, if they're national or multinational.
Okay, thanks, Brian.
If I can add to what Brian just said, I think from our perspective at Bloom, we're looking at generally lower temperature applications making more sense for electric. It just becomes a little bit impractical as you get to the real high temperature applications. The other thing is, if you think back to Michael's presentation where he showed the different carbon footprint for electric in different regions, that's something you really need to consider. So for instance, switching a natural gas fired furnace in, say, China to electric would actually dramatically increase your carbon footprint. Versus if you could eliminate a natural gas fired furnace in Sweden and switch to electric, you could almost eliminate your carbon footprint. It just depends on how that energy is being made.
Good point.
Thanks, Stephen.
I'll jump in on that question too, just to help the fundamental learning. If you think about the furnaces and the heating systems for the furnaces between electric and natural gas, from a fundamental heat transfer perspective, you have to have a temperature differential between items to drive heat transfer. That's obvious. And the governing limitation on a lot of electric heating is the temperature to which you can drive an electrical resistance element. You have a theoretical flame temperature, for example, on natural gas at 3,500 degrees. It's hard to get materials that'll stay alive over 2,000 degrees under electrical resistance heating. So a lot of the why in the last two speakers' answers of why does electric make more sense in lower temperature furnaces, it's because you got to have a temperature differential somewhere to drive the heat transfer. Once you get into temperatures or furnaces over like 1,400 degrees Fahrenheit, radiation really does take over as the dominant heat transfer mechanism. And so your source of heat then becomes very important in terms of driving that. So electric versus fossil fuel combustion, generally fossil fuels win as the temperature goes up. Obviously, the advantage to electric is no stack losses. Right? So again, very dependent on the process, very dependent, but electrification is definitely one of the tenets of sustainability and a carbon-free environment in the future.
Okay, thank you. So next question here, are RTOs a potentially good application for oxy-burning?
Back on the oxygen topic, I'll take that one again. Absolutely. From the perspective that the thermal destruction of any waste product, be it solid, liquid, or a fume-based waste, oxy-fuel combustion makes everything volatile. The very, very high temperatures are advantageous in destruction of materials. I can think of a few trace applications that came out of the oil and gas industry where oxyfuel was useful in a RTO type application. But yeah, conceptually, yes. Is there a big body of it? No, primarily because of the added operating cost of generating the oxygen. But in places like refineries, where you're doing all kinds of process separation and you may have a source of available oxygen, yeah, it can make a lot of sense.
Okay, great. So with oxyfuel and hydrogen combustion, how will you deal with the higher water content in the exhaust?
Also an excellent question. I think the fundamental quick answer is via temperature. You will have higher water content. There's no question from a concentration perspective, not necessarily from a total mass flow perspective, but typically keeping the exhaust gases hot so that you don't generate any condensation. Then you also have to be mindful about the chemistry of a particular process. If you have higher water content, even in a gaseous form, can the product and the process accept that? Again, something that has to be analyzed. But generally, we don't worry much about the added water content in most applications as long as the exhaust remains above condensation temperatures.
Okay, a couple more questions here I think we have time for. Oxy-combustion with carbon capture may have acceptable economics if a carbon tax comes into play and you have to capture carbon in some industrial processes. Is that a good statement?
That is a fair statement. And for example, if I think back about some of the research work that was done in oxy coal combustion, that was very much the driving motivation. When you have a massive reduction in the total mass flow, 80%, by taking the nitrogen out of combusting coal, it's much, much easier from a carbon capture perspective to deal with a volume of gases that's 1/5 of the size of air fuel combustion. So yeah, very, very solid connection in thinking there. Again, not something that I'm aware of that's actually being done yet today.
Okay, yeah, and along the same lines, just another statement, carbon capture is more cost effective with a concentrated carbon dioxide stream. So
Correct.
yeah, okay. Well, if there are no further questions, we are going to wrap it up here, and thank you all for attending the webinar today. Remember, you will get a link to the recording, so if you missed things and want to review again, please feel free to hop on the IHEA website, www.ihea.org, and you will find all of the recorded webinars there, along with more resources and information on sustainability and decarbonization. So just watch for a link to the survey for us and take a few moments to share your feedback, and have a great day, everybody. Thank you.